for JFET. Now we will solve some problems on JFET. And N-channel JFET has IDSS equal to 2 milliamperes and Vp equal to -4 volt. Calculate its transconductance Gm when VGS equal to -2 volt. This question was asked in GATE 1999 in electronics paper. We know that transconductance of JFET Gm is equal to -2 IDSS upon Vp into 1 minus VGS upon Vp. Putting all the values, we can get the transconductance of JFET as -2 into 2 milliamperes divided by -4 volt into 1 minus -2 by -4 volt. Solving this, we get -4 into 10 raised to power -4 divided by -4 into 1 by 2. It will be 0.5 millisiemens. Next question. Calculate the drain current ID for JFET with Vp equal to -4 volt and VGS equal to -2 volt with IDSS. This JFET has IDSS equal to 10 milliamperes. Now ID, drain current ID equal to IDSS into 1 minus VGS upon Vp. This simple equation equals to what? This equation can be used to calculate ID. IDSS is given 10 milliamperes and 1 minus VGS is given -2 volt divided by -4 volt whole square. This will be equal to 2.5 milliamperes. This will be drain current ID at VGS equal to -2 volts. Next, calculate transconductance Gm when ID changes from 3.1 milliamperes from 1.3 milliamperes to 1 milliamperes with change in VGS from -3 volts to -3.1 volts. Transconductance Gm. We know that transconductance Gm equal to del ID upon del VGS at constant VDS. Using this equation, I can write this change in ID equal to ID2 minus ID1 and this change in VGS as VGS2 minus VGS1. ID2 is 1 milliamperes and ID1 is 1.3 milliamperes, while VGS2 is -3.1 volt, and VGS1 is minus 3 volt. So minus of minus 3 volt. It will be minus 0.3 into 10 raised to power minus 3 divided by minus 0.1 volt. This will be in ampere. It will come out to be 3 millisiemen. This will be the transconductance GM for this JFET. So this was all about JFET. Now we will move to MOSFETs, metal oxide semiconductors. But before moving to the MOSFETs, we will discuss something about MOS capacitor. MOSFET's operation is somewhere depends on this MOS capacitor. MOS capacitor has a simple structure. It has a P-type or N-type semiconductor on which an insulating layer is developed, which is silicon dioxide SiO2 insulating layer. And above this metal plate will be there. And nowadays in modern MOSFETs, this metal plate is not used. Instead of this metal, P plus polycrystalline silicon is used. Silicon is used. If it is N-type substrate, then it will be N plus polycrystalline silicon. So in this structure, this upper part is metal, middle part is SiO2 insulating layer, and the lower part is a semiconductor. So this structure is called metal oxide semiconductor MOS. And this terminal is, we will call this as gate terminal, and this terminal will be grounded. This will be called as body terminal for this MOS capacitor. Now we will see the operating modes of this MOS capacitor, which will be later on used in MOSFETs. Depending on the voltage at the gate terminal, that is voltage VG, a MOS capacitor operates in 3 different modes. Number 1 is accumulation mode. We have a MOS capacitor with P-type substrate, and this substrate is kept at ground terminal, ground potential, while we will apply a negative potential at this metal terminal, gate terminal. If we apply a negative potential to the gate terminal, then the gate metal will be negatively charged, and this negatively charged gate metal will attract the positive charges that are holes near this oxide semiconductor interface. Near this oxide semiconductor interface, this is nothing but accumulation of holes when negative potential is applied. So a MOS capacitor will operate in accumulation mode when a negative gate potential is applied, that is Vg is negative. Now in accumulation mode, we can see that this particular region is conducting region, this particular region is conducting region, while in between these two conducting region there is non-conducting region, so it can be seen as a parallel plate capacitor. If this is the thickness of oxide layer, then in accumulation mode the capacitance of this MOS capacitor will be oxide capacitance, and it will be written as epsilon A by P oxide, where epsilon is equal to epsilon naught into epsilon r, epsilon naught equal to 8.854 into 10 raised to power minus 12 farad per meter, or it will be equal to 8.85 into 10 raised to power minus 14 farad per centimeters. While epsilon r is the relative permittivity of SiO2, permittivity of SiO2, and it is equal to 3.9. Now the capacitance can also be written as C oxide equal to epsilon upon P oxide. Here we have not considered this area, so the oxide capacitance can be written as farad per meter square in this case, and here the unit of capacitance will be farad. So in accumulation mode, when a negative potential is applied to the gate terminal, the positively charged carriers of p-type substrate will be accumulated near oxide semiconductor interface, and this mode of operation is called accumulation mode. If we have n-type substrate instead of p-type substrate, then to operate it in accumulation mode, we must apply a positive voltage at the gate terminal. So this positive gate metal will attract negatively charged electrons in this region. In this case, the accumulation will be due to electrons. Now the second mode of operation is depletion mode. Now this time we will apply a positive voltage, Vg will be positive, but this voltage will be less than voltage which will be defined later called threshold voltage. If the applied gate voltage is less than threshold voltage, then the gate metal will be positive, but this positive voltage is not sufficiently strong to this is p-type substrate. This positive gate metal is positive voltage to the gate metal is not sufficiently strong to attract the negatively charged carriers, which are very less in this p-type substrate. So this voltage is sufficient only to repel the holes away from the oxide semiconductor interface. If these holes are repelled away, then such a region will form here where there will be no charge carrier, there will be only ions. So a depletion layer will form. depletion layer will form, and this mode of operation is called depletion mode. This is the oxide layer, and this is width of depletion layer, that is extreme. Now we can see this is the conducting region and this is the conducting region. Now all the charge carriers in this particular region are repelled away, and because there are no charge carriers in this region, we can say that this region is also a non-conducting region along with this. So there will be two capacitances, one capacitance in oxide layer, other capacitance due to this depletion layer. There will be two capacitances in series. One capacitance will be oxide capacitance, other capacitance will be depletion capacitance, which will be called CD. The oxide capacitance we already have seen equal to epsilon upon T oxide, and it will be written as epsilon naught into epsilon R of SiO2 divided by T oxide farad per meter square. The depletion capacitance will be written as epsilon upon XD, width of depletion layer, and epsilon will be epsilon naught into epsilon R, but is in case of silicon, because this is not silicon oxide, it is silicon material which is a part of this p-type substrate. So divide by XD, this will be the capacitance due to depletion layer in farad per meter square. The total capacitance in depletion mode will be C equal to 1 upon the total capacitance C is the series combination of both the capacitances, will be written as 1 by C equal to 1 upon C oxide plus 1 upon CD. So total capacitance C will be equal to 1 upon C oxide plus 1 upon CD. It can also be written as C oxide into CD upon C oxide plus C. This will be the total capacitance in depletion. Now the third mode of operation is called inversion mode. This is more important than the other two modes of operation. Inversion mode. This time again we will apply a positive voltage to the gate terminal, but this time this voltage will be greater than this threshold voltage. Threshold voltage, if the applied voltage is greater than threshold voltage, then this voltage, applied gate voltage, will be sufficient to attract the negatively charged carriers, which are very less in this p-type substrate. So these electrons will be attracted towards oxide semiconductor interface, and now there is no depletion layer in this particular operating mode. So this time there will be only oxide layer, non-conducting layer. So the capacitance will be equal to C oxide equal to epsilon Si epsilon naught into epsilon R of SiO2 divided by so this will be the total capacitance of most capacitor in inversion mode. This is the inversion layer of electrons. If it is n-type substrate, then inversion layer will be due to holes. Now we will draw the capacitance for most